Right, so we have to discuss question number 8, 9, and 10. So I'm not taking much of a time to minimize the timing and everything. So we'll just go through this. So very similar to other questions. Question number 8 is always going to be related to some inorganic, qualitative, and quantitative analysis. So the first part is qualitative. So solution Y contains 3 cations. So they have given some test to identify these cations, right? So we will check what are the tests and observations. So dilute HCl was added to a small portion of Y, a white precipitate. So you know this white precipitate can be from Ag plus, AgCl, and can be from Pb2 plus, PbCl2, this is lead, and also it can be from mercurous, Ag2, 2 plus, so Ag2Cl2. So one of these, or maybe 2 or even 3 can be the cations that is present in solution Y. We don't know 1, 2, or 3. Then P1 was separated by filtration. Okay, so this precipitate was separated. So we don't know which cation is present here. And H2S was bubbled through the solution. So the filtrate. And a black precipitate is formed. So remember, this condition is now acidic. So what are the precipitates that form in the acidic medium when H2S is bubbled? We know about 9 precipitates. So we have to figure out what are the black precipitate from that. So basically we have Ag2 plus, mercuric, Ags, and even lead also, lead 2 plus, Pb2 plus. So you have to understand all lead 2 plus is not precipitated here. Some can be precipitated here also. And copper 2 plus, and bismuth, Bi2S3 also can be formed, right? Bi3 plus also can be present here. And they have filtered this solution and removed H2S, and they have added some ammonium hydroxide, ammonium chloride. So this gives the idea they have added this to form any hydroxide without the oxidation, right? Because in the third step of our cation analysis, we first add H10O3 to oxidize whether if there is some Fe2 plus, we add HNO3 to oxidize them into Fe3 plus, but that step is not done. Anyway, we have no problem here because we haven't seen any precipitates forming, so no problem in that. But when H2S was again bubbled, now the condition is basics, they were able to see again black precipitate, right? So what is the black precipitate that here? This is group 4 now. So group 4, we have mainly cobalt sulfide. So cobalt 2 plus and nickel 2 plus. And zinc and manganese. So zinc and manganese are different colors. So black precipitates were these two, right? So we can expect like 1, 2, 3, 4, 5, 6, 7, 8, 9 cations, out of which only 3 is available in solution Y. So we have to move on to the next one, right? Then what we have that they have done is for the precipitates that they form in P1, P2, P3, they have done some other separate tests, right? So P1 was water was added to P1, okay, then the mixture was boiled. So a part of P1 dissolved. So this gives you the idea. Normally we know Pb2 plus, they dissolve at hot water, right? So surely this P1 contains Pb2 plus. That is one solution, one conclusion that we can draw, right? So this mainly is due to our Pb2 plus, right? And the mixture from one above was filtered, okay, and the following tests were carried out. So the filtrate, so basically the filtrate should contain this one. And when you add dilute H2SO4 to warm F1, a white precipitate. So basically it is lead sulfate. The residue, which can be either Ag plus or Ag22 plus, because these two cations will not dissolve under warm hot. So we have to check what is that those two, either it can be Ag plus or Ag22 plus. So the residue first washed thoroughly with warm water, okay, and dilute ammonia was added and R1 dissolved. So if you can remember, we have already discussed when you have ADCl and when you have this dilute ammonia, it forms the silver amine complex, silver diamine complex. So this will form the silver diamine complex, which dissolves and forms the complexation, right? So this gives you the idea this should be silver plus here, right? And it was confirmed. See here, when Ki was added, dark yellow precipitate. So you know this is AgI, which is very dark in color, dark yellow. So we confirm one is Pb2 plus, the other one is Ad plus, right? And the second, for the second precipitate, where again it can be lead, silver, lead, mercuric, copper, bismuth. So we have done some experiment. P2 was dissolved in warm diluted HNO3. Okay, so it dissolved these precipitates normally dissolve sulfides, and potassium chromate solution is added, a yellow precipitate is formed. So this directly gives us the idea lead chromate is formed anyway in this one, because others, these other cations does not give you a yellow color. Okay. And finally, for precipitate 3, which we think either it can be cobalt or nickel. So P3 was dissolved in warm concatenation O3, so a pink color. So we know that cobalt in the, when it is dissolved, either in the aqueous media, it gives a pink color. Nickel is generally greenish blue color. So surely this should be cobalt. So we can write this as H2 or 6, 2 plus. Okay. Cobalt H2O6 2 plus. You can write that in that way. And the following way added to the solution one above. Okay, so the cobalt 2 plus solution, concave Cl, a blue color. So you know this is COCl42 minus. You should know at this point. And when you add diluted ammonia, a yellow brown color solution, that is the chromic hydroxide that can be formed. And when you have more and more ammonia, it will form cobalt, NH3, 6, 2 plus. This is which gives the yellow brown color solution. Okay. Initially it forms the precipitate, then when you add more and more ammonium hydroxide, so it will dissolve and form this amine complex. Identify the 3 cations. Reasons are not required, although we have discussed the reasons. They don't expect you to write down all the reasons. So we have in this one Ag plus, Pb2 plus, and also what is the other one? It is cobalt. So those are the 3 cations. Precipitate P1, P2, P3. So basically precipitate P1 is AgCl, PbCl2, and precipitate 2 is PbS, and finally this is cobalt sulfide, COS. Okay. Species responsible for the colors of the solution. So solution 1, you can write this hexa aqua complex. 2 is COCl42 minus, you can write this down. And finally, the amine complex with 2 plus. So all these are very simple things. Okay. Explain briefly why the cations that precipitates in A4 above does not precipitate in acidic media. So I have already explained this to you many times. I told you this basically depends upon the S2 minus concentration, the precipitation, and you can show the equilibrium of H2S in aqueous medium, show the physical states, H plus and H minus. This is the first equilibrium, and you can show in the second. Just put this negative, that is fine. And then another H plus S2 minus, right? Then you can explain in the acidic medium there is more H plus, so that S2 minus concentration is minimized. This equilibrium is shifted towards the left hand side. There will be a minimum S2 minus concentration. Therefore, in the group 2, only precipitates, the salts with lower KSP values get precipitated. Okay, but in group 4, where A4, you can mention the medium is basic, so this H plus is removed from the OH minus, so there is a higher S2 minus concentration. So the precipitate that form in A4 are with higher KSP values, right? So why this precipitate does not form in acidic medium? Because S2 minus concentration is not enough to exceed the KSP values of precipitates. That is it of these precipitates which are formed at group 4. Okay. So this is a very nice question where cation analysis was tested. And this is the end of the qualitative lesson. So we have to go to the quantitative part now. Right. So we have given a quantitative part. A solid sample was found to contain ammonium sulfate, ammonium nitrate, and non-reactive substances. And the following procedures were used to determine. Okay. So 1 gram of this solid sample was dissolved in water, and it was diluted up to 250 cubic centimeter. And this solution is called solution S. So it will have a certain concentration of this, and there will be some non-reactive species as well. And they have carried out 2 procedures here. Procedure 1 is 50 cubic centimeter of solution S was treated with an excess amount of strong alkali, and certain gas is liberated, and this was passed through HCl. And to neutralize the remaining amount of HCl, they have used some NaOH, and 10.2 cubic centimeters were required, right? And in the second procedure, what they have done different from the first procedure is the volume is reduced a little bit. They have used 25 cubic centimeter, and they have added aluminium powder, and the rest is very similar. And finally, the NaOH volume required to remain titrate the remaining HCl was 15 cubic centimeter. Right? So they have given a note, so it was checked by litmus paper. So they have identify the gas liberated in procedure 1, identify the gas liberated in procedure 2, write the Barnes chemical equation for the reaction taking place in procedures 1 and 2, and finally calculate the mass percentage of each compound. So you can, if you know the mass of this and this separately, so you know the total mass, that is 1 gram, then you can multiply it by 100 to get the percentages of this, right? So to minimize your time consuming, I have drawn this entire procedure as a summary in the board, right? So you can see this is the solution S, 1 gram to 150 cubic centimeter. And in the first procedure, they have taken 50 cubic centimeter from solution S. So this is solution S. And they have added excess NaOH, so some gas is released. And to neutralize this gas, they have used 30 cubic centimeter of 0.1 mHCl. And to neutralize the remaining, they have used 0.1 mMH. 10.2 cubic centimeter was consumed, right? And here this is the same thing, second procedure, but only difference is they have added some aluminium powder. So if you can remember, if you can think about that a bit, why aluminium powder is added. So think about that. So the first thing is to identify what is this gas that is liberated. So for that, we need to understand what are the reactions that is happening, right? So basically here, here you have ammonium sulfate and ammonium nitrate. So which ammonium sulfate is going to give some ammonium plus, right? And in the same way, ammonium nitrate is also going to give some ammonium plus. This ammonium plus with NaOH, you know, it will going to liberate ammonia gas. So that is the main reaction. So if I tell about this step one, maybe, or procedure one, the reaction that is going to happen is first ammonium sulfate. See here, ammonium sulfate with NaOH. It is going to give sodium sulfate and sodium sulfate and ammonium hydroxide. So basically ammonia and water. This is what going to happen, right? So I'll put 2 here, and there will be 2 ammonia here to balance the nitrogen and 2 water to balance the oxygen. This is one of the reaction that is going to happen, ammonium sulfate with NaOH. The other reaction will be ammonium nitrate with NaOH in the same way. So it is going to give NaNO3 plus ammonia plus water. Right. So these 2 reactions are going to happen in the procedure 1, right? But in procedure 2, think about this. In procedure 2, the same reagents are there, and when you add excess alkali, these 2 reactions are automatically going to happen. So if I put this as 1, 2, in procedure 2, 1, 2 is automatically going to happen, which means these 2 reactions are going to happen. But additionally, you have to remember there is nitrate here. This is the very important point. This nitrate, if you can remember, with aluminium powder, so this can be either aluminium or Devadas alloy, we say, is going to give again ammonia, if you can remember. So from these 2 reactions, again, this will give some amount of ammonia as using these 2 reactions. And additionally, if you can remember, there is another reaction that is happening. Nitrate is going to reduce towards ammonia, while aluminium is going to aluminate. Okay, oxidation reduction reaction is going to happen. And we have already balanced this equation, and we have discussed what is actually happening in the previous papers as well. So the overall reaction, if I write the overall reaction that is happening here, is I will write here somewhere here, 5OH minus is going to react with 3NO3 minus and 8 aluminium, and I will write here 2H2O is going to give you 8AlO2 minus and 3 ammonia, right? So this is our third reaction from procedure 2. So now think about the fact, the difference between these 2 procedures. Because in procedure 1, we know these 2 reactions happens. In procedure 2, we have these 2 reactions plus an additional reaction. So if you find the total ammonia that is formed here in procedure 1, it is mainly from these 2 reactions. And if you find the ammonia amount released from procedure 2, it is mainly from these 2 reactions plus the additional amount that is formed because of the nitrates, right? So when you subtract the amount of ammonia that is formed in this procedure 2 minus procedure 1, to get the amount of nitrate present directly in the sample, right? For that, they have given this piece of information. Because from this, you can calculate the the amount of HCl added, right? So 30 into 0.1 means 3 into 10 to the power minus 3 moles. Okay. When you get the stoichiometry 1:1, because the ammonia gas here with HCl, it is 1:1 stoichiometry, right? So this is the amount HCl added, and this is the remaining amount. Still, stoichiometry is 1:1. So this will be like 1.02 into 10 to the power minus 3 moles. And when you subtract this by this, you get the amount of ammonia released from procedure 1, basically. And you can do the same here. This will give you the remaining amount for procedure 2, and this will give the remaining amount, so the added amount of procedure 2. So again, this is same, 3 into 10 to the power minus 3 moles. And here this is 1.5 into 10 to the power minus 3 moles. Okay. And when you subtract this by this, so basically here 3 minus 1 is 2, 2 minus, this is 1.98 into 10 to the power minus 3 moles. So this is the ammonia from procedure 1, 1.98 into 10 to the power minus 3. And here the difference will give you the amount of ammonia released from procedure 2. Okay, so this is procedure 1 and this is procedure 2. And here it will be 1.5 into 10 to the power minus 3 moles ammonia. So you know the amount of ammonia that is released from procedure 1 is this, and procedure 2 is this, right? If I am correct. Yeah. So how do you calculate the ammonia that is given away from this nitrate? Because if you know this ammonia, this should be equal to nitrate, because the stoichiometry is 3:3, which means 1:1. It's like 1:1, right? But don't forget, here we have calculated 1.5 into 10 to the power minus 3 moles of ammonia released from procedure 2 for 25 cubic centimeter of solution, right? Because here they have used 50. Volume is changed. So first you have to calculate here this for 50 cubic centimeter. So it will be 3 into 10 to the power minus 3 moles, right? And then you can subtract this 3 into 10 to the power minus 3 moles of ammonia from procedure 2 minus 1.98 into 10 to the power minus 3 moles from procedure 1. So 3 minus 1 is 2, and 2 minus 0.98 is 1.02. So 1.02 into 10 to the power minus 3 moles of ammonia is released from nitrate. Because the stoichiometry is 1:1, you can equalize this to the number of moles of nitrate present in this solution S. Right? So if you know the number of moles of nitrate in solution S, then you can multiply it by the molecular weight of ammonium nitrate, which is 80. Then you can calculate the mass. Then you divide it by 1 gram and multiply it by 100. Then you get the mass of it as percentage, actually. Okay. So you know the mass percentage of this. And you know the amount of moles that is from 1.202 into 10 to the power minus 3 moles as well. Then how to calculate the mass percentage of this one, ammonium sulfate? This becomes now very easy, because in the first step you know that the ammonia is given away from this ammonium nitrate as well as ammonium sulfate, right? So you know this total amount, and this total amount that is from this first step procedure 1 was 1.98 into 10 to the power minus 3 moles. Because ammonium plus and nitrate, this ratio is 1:1. So the ammonia that is given here is this, and ammonia from this is this. But you already know how much amount of ammonia is given from ammonium nitrate. You know that, right? That is a calculation that we did, and it is already known. This is this amount. Because when you do the reaction, you know, sodium nitrate is going to form, ammonium plus water is going to form, ammonia and water is going to form. So this total amount is this 1.98 into 10 to the power minus 2, right? And ammonium nitrate is this. So you can calculate how much ammonia is formed from ammonium sulfate. So you are going to know this one. This one will be 1.98 into 10 to the power minus 3 minus 1.02 into 10 to the power minus 3 moles. So you know the amount of ammonia that is given away from ammonium sulfate. And one last step, this stoichiometry between ammonia given from ammonium sulfate and ammonium sulfate is 2:1. So finally, to calculate the moles of ammonium sulfate, you have to divide this 1.98 10 to the power minus 3 minus 1.02 10 to the power minus 3 divided by 2. So you get the number of moles of ammonium sulfate in solution S. Then you multiply it by the molecular weight, divide it by the mass, 1 gram, multiply it by 100 to get the mass percentage. Okay, so I hope this is clear, right? Not a difficult one, just you have to remember the specific test that we use for nitrate. I think I have told you like 100 times now. Okay, so I will share the screen again. Right, so basically this is ammonia, and the reactions are given here and the mass percentages can be found. Okay, so this is very nice question.